morning, students. Welcome to another lecture on control systems engineering. In the previous session we have discussed about what is a control system engineering, types of control system engineering like open loop control system, closed loop control system and feedback networks, and we have also discussed about the advantages and disadvantages of open loop and closed loop control systems. In today's class we are going to discuss about the mathematical models of control systems, mechanical control systems, and what are the types of mechanical control systems, and we are going to discuss about the types of symbols and the list of symbols what we are going to use in mechanical translation system, and we are going to perform one or two problems in the regarding that mechanical and translation systems. Coming to mathematical system, so the set of mathematical equations describing the dynamic characteristics of a system is called mathematical model of the system. That means we are defining some mathematical equations for describing the dynamic characteristics of the system. Here we have two types of system, that is a mechanical system as well as electrical systems. So in mechanical systems present we are going to see the mechanical system. In mechanical system there are two types of mechanical systems are there. One is mechanical translation system and the other one is mechanical rotational system. So initially we will go for mechanical translation system, and we will discuss what are the terms and conditions, or what are the terms we are going to use in this mechanical translation system. Here the input to the mechanical translation system is a force and the output of the mechanical system is a displacement. That means here we are applying some force to the mass or body, and that force will move the given mass or body, or move the mass or body to some extent, that is it's a displacement. So see, mechanical translation can be obtained by using the three basic elements that are mass, dashpot as well as spring. That means here we are taking three terms, that is mass, dashpot and spring. So list of the symbols what we are going to use in the translation system mechanism are X which is used for the displacement, and V which is used for velocity and also acceleration. So here by X can be represented as the displacement, X can be represented as displacement of the system, and V will be represented as velocity of the system, and A is equals to acceleration, which can be represented as here C, displacement, and the relation between displacement and velocity is equals to derivative of displacement. And coming to the acceleration is equals to derivative of the velocity. That means see here we have a displacement of x, and when we go for velocity we have dx by dt, and when we go for acceleration we have a d square x by dt square. So these are the terms and the symbols which we are going to use in mechanical translation system. And F is the applied force, and also Fm is the opposing force offered by the body offered by mass of the body. That means whenever we are moving a body, or whenever we are applying some force on a body, the body will definitely opposes. Then that force we are taking it as an opposing force, and Fk is nothing but opposing force offered by the elasticity of the body. It is also called as a spring. And coming to the Fp, it is the opposing force offered by the friction of the body. It is also called as a dashpot. Okay, and M in terms of the mass will be in terms of kilograms, and K is the stiffness of the spring in terms of newtons per meter, and B is the viscous friction coefficient in terms of. Okay, so the lowercase letters are the functions of time. Coming to the mass, what is mass and how it is going to be, see here we are applying some force here we are applying some force, that is we are applying F force to the mass m, and here x is nothing but the displacement. See, let F is the applied force and Fm is the opposing force. Here whenever we are applying some force to this body mass, it automatically opposes, that is nothing but opposing force due to mass. Fm is nothing but opposing force due to mass, and here Fm is directly proportional to d square x by dt square. So therefore Fm is equals to mass into d square x by dt square. So by Newton's second law, F is equals to ma. Here a is nothing but acceleration in the previous where acceleration is equals to d square x by dt square, which compares to displacement. So coming to dashpot, what is a dashpot and how it is going to be applied? See here, here we have applied a force F with some displacement x. See here the dashpot. Before, sometimes we may have two dashpots also. See here, so the applied force is F and the displacement is x, and B is the dashpot. So FB is the opposing force due to friction. Therefore hence FB is directly proportional to dx by dt, and FB is equals to B into, that means dashpot, B into dx by dt. By Newton's second law, F is equals to Fb is equals to B into dx by dt. In some cases we have two dashpots, that is here, see here, we have x1 as well as x2, and at that particular time Fb is directly proportional to d by dt of x1 minus x2. Coming to the it can also be written as Fb is equals to B into d by dt of x1 minus x2, and as we have also shown that F is equals to Fb is equals to B into d by dt of x1 minus x2. Coming to the spring, what is a spring here? See, mass, dashpot and spring are the terms which we are going to use in mechanical translation system. See here we have applied force and we have a spring here with respect to reference, and here F is the applied force and Fk is the opposing force due to elasticity. Here Fk, that is this Fk is directly proportional to x, and it can be also represented of Fk is equals to k into x, and by Newton's formula F is equals to Fk is equals to kx. As we have already seen in the previous slide that where there may be a possibility of one or more dashboards. The same sense that here we have two springs, that is x1 and x2. If two springs, one or more springs are available, then Fk is directly proportional to x1 minus x2, and Fk is equals to k into x1 minus f2. According to Newton's second law, F is equals to Fk is equals to k into x1 minus x2. So what are the Laplace formulas we are going to use for this? See, Laplace transform of x of t, which is nothing but our displacement, is given as x of s. Here x of s is also called as the output of our system. See here, Laplace transform of d by dx of x of t can be written as Laplace transform of d by dx of x of t at zero initial conditions can be written as s into x of s. At see, in the same sense, the Laplace transform of d square, here this is velocity and this is acceleration. Laplace transform of acceleration can also be written as L of d square by dt square of x of t is equals to s square into x of s. We need to remember all these formulas for performing problems. So first of all we'll check for one problem, that is write the differential equation governing the mechanical system below, determine the transfer function. So in order to find the transfer function, we need to find the differential equations first. See here we have two mass elements here, m1 and m2, and force is applied to m2 only but not for m1. So in order to obtain the transfer function, we need to design the free body diagram and we need to find out the differential equations. After that we'll see what will be the procedure. So in the given system, the applied force is, as I have already told you, that the applied force is f of t and the displacement is x. See here the applied force is f of t and the displacement is x. So the Laplace transform of f of t is equals to Laplace transform of f of t is equals to f of s, and the Laplace transform of x, that is displacement, is equals to x of s. So in order to find the transformation function, we have to take the ratio of output to the input, that is x of s to the f of s. So let the displacement of the mass m1 be x1. So I'll just see here. So initially, as we have already seen, that we have two mass elements, that is m1 and m2, where first of all we are considering m1. Let the displacement of the mass m1 be x1. As we in the previous slide we have seen that displacement is x and force is f1, which was connected to the mass element 2, that is m2. Here m1, we are assuming that x1 is the displacement of this m1. Then the opposing force acting on mass m1 are marked as, so these there is no input force here, input source is here. No force is applied to this m1, as I have already told you. The opposing forces are fm1, fb1, fb, fk1 and fk are the opposing forces, and x1 is the displacement. So as we have already seen that fm1 can be written as m1 into d square x1 by dt square, and fb1 is equals to b1 into dx1 by dt, fb equals to b into d by dt of x1 minus x, and fk1 is equals to k1 x1, and fk is equals to k into x1 minus x. So these are the differential equations for m1. So by Newton's second law, we know that F is equals to ma, that is force, applied force is equals to sum of the opposing forces. Here, as we have seen that there is no force is applied to m1, that's why m1 is equals to, so here no force has been applied, that's why we have written as 0, and these are the opposing forces. Applied forces is equals to opposing forces. Therefore, so m1 d square x1 by dt square plus b1 into dx1 by dt plus b into d by dt of x1 minus x plus fk1 is nothing but k1 x1 plus fk is nothing but k into x1 minus x2 is equals to 0. So on taking Laplace transform on both sides, we have m1, so d square x1 by dt square can be written as s square x1 of s. The same sense, dx1 by dt can be written as b1 into s into x1 of s plus this one bs into x1 of s minus x of s plus k1 x1 of x plus k into x1 of s minus x of s is equals to 0. So by taking m1 of s as common, m1 of s is equals to m1 s square, x1 of s as common. See here, here we have taken x of s as common, x1 of s here is there, it is also here, it is also here, it is also there, and it is also there. So by taking x1 of s as common, m1 s1 square, m1 s square plus b1s plus bs, in the same sense, okay, b1 plus b into s plus k1 and k and minus x of s. If we take minus x of s, bs plus k is equals to 0. Therefore x1 of s is equals to x1 of s into, we are taking this line into right side, so x1 of s into m1 s square plus b1 plus b of s plus k1 plus k is equals to x of s. We are taking this one into right, we are taking this value to the right side. That means so that it has become x of s into bs plus k. So therefore we need only x1 of s. What is our output? That means this is our output value. Why? Because this is our displacement for mass 1. Therefore x1 of s is equals to x of s, x1 of x is equals to x of s into bs plus k by m1 s square plus b1 plus b into s plus k in 1 plus k. So the opposing force is acting on m2. Now we'll go for m2 or fm2, fp2, fb and fk, and the free body diagram is here. This is applied force and these are opposing forces. I repeat, this f of t is the applied force and these are the opposing forces, and x is the displacement. So fm2 is equals to m2, opposing forces fm2, fp2, fp and fk. fm2 is equals to m2 into d square x by dt square, fp2 equals to b2 into dx by dt, and fb is equals to b into d by dt of x minus x1, and also fk is equals to k into x minus x1. And by applying Newton's second law, see here in the previous circuit or in the previous slide we have applied force equals to 0 there, but here we have applied force and we have opposing forces. So f of t is the applied force, fm2, fp2, fb and fk are the opposing forces. Therefore f of t is equals to m2 d square x by dt d square x by dt square plus b2 into dx by dt plus b into d by dt of x minus x1 plus k into x minus x1 is equals to f of t. And by taking Laplace transforms on both sides, it will be like this. That is m2 s square of x of s plus b2 s x of x plus bs x of xs minus x1 of s plus k into x of s minus x1 of s, which will be equals to f of s. So by taking x of s as common, x of s into m2 s square plus b2 plus b into of s plus k minus x1 of s into bs plus k is equals to f of s. As we know that in order to obtain the transfer function, it can be written as x of s by f of s. Therefore x of s by we have already know the value of x1 of s. In the previous one we have known the value of x1 of x is equals to b of bs plus k by m1 s1 square plus b1 plus b of s plus k1 into k. So by substituting that one, we have x2 m2 s square plus of b2 plus b of s plus k minus x of s into bs plus k whole square by m1 s1 square plus b1 plus b into x plus k1 plus k is equals to f of x. So by taking the LCM, we have this equation, and therefore the final value will be the transfer function is x of s by f of s. Therefore x of s by f of s is equals to, as it is a reminder, if it goes to here it will be numerator and it will be as it is denominator, it will be numerator and this will be your denominator. Therefore the transfer function is x of s by f of s is equals to m1 s square plus b1 plus b of s plus k1 plus k by m1 s square plus b1 plus b of s plus k1 plus k into m2 s square plus b2 plus b of s plus k minus bs plus k whole square. And the resultant are, we need to find the differential equations, and then we need to find the Laplace transform of those differential equations. I see here the differential equations are m1 d square x1 by dt square, b1 dx1 by dt plus b into d by dt of x1 minus x plus k into k1 x1 plus k into x minus x is equals to 0. This is one differential equation, and this is another differential equation. And the transfer function is f of x of x by f of s is equals to m1 s square plus b1 plus b of x plus k1 plus k by m1 s square plus b1 plus b of s plus k1 plus k into m2 s square plus of b2 plus b of s plus k minus bs plus k whole square. So this is the required transfer function. What they have given initially, to find the, so write the differential equation and also determine the transfer function. So here we have written the differential equations. We have find the differential equation as well as find the transfer function. We will go for another problem. Determine the transfer function y2 of s by f of s in this given system. That means here we have a C. In this system we have two mass elements m1 and m2, and the applied force is only for m1, and the displacement for m1 is y1 and the displacement for m2 is y2. So we need to calculate the transfer function, that is y2 by f of s, that is f of t. See here, so let the Laplace transform of f of t is equals to f of s, and the Laplace transform of y1 is equals to y1 of s, as we have two mass elements, two displacements, y1 of s and y2 of s. So the opposing forces are marked as m1, fm1, fb, fk1 and fk2. So first of all we are going to draw the free body diagram for m1. So here the applied force is f of t and the opposing force of fm1, fb, fk1 and fk2, and the displacement is y1. Therefore fm1 is equals to, we are calculating the opposing forces, fm1 equals to m1 mass m1 with respect d square y1 by dt square, fb is equals to b into dy1 by dt, and fk1 equals to k1 into y1, and fk2 is equals to k2 into y1 minus y2. So by applying Newton's second law, the applied force is equals to opposing forces, that is applied force is nothing but f of t, and the opposing forces fm1 plus fb plus fk1 plus fk2. So substitute those values here. fm1 equals to m1 d square y1 by dt square plus fb equals to b into dy1 by dt plus fk1 is nothing but k1 into y1 plus fk2 is equals to k2 into y1 minus y2, which will be equals to the applied force, that is f of t. And by taking Laplace transform on both sides, that can be written as f1 s square of s square y1 of s plus bs into y1 of s plus k1 y1 of s plus k2 into y1 of s minus y2 of s, which will be equals to f of s. So we need to find the transfer function. So therefore f of s is taken, f1 of s is taken as common here. So as we have seen everywhere here, so we have taken f1 of s is common, and the output will be m1 s1 square plus bs plus, as we have taken y1 as common, k1 plus k2 plus k2, and minus y2 of s into k2 is equals to f of s. As we know that we need to find the output of the transfer force, that is y1 of s by f of s. The opposing forces for m2 also we are going to calculate. So opposing forces for m2 are fm2 and fk2. So the free body diagram for m2 is applied force is 0 and the opposing force are fm2 and fk2. Therefore fm2 is equals to m2 into d square y2 by dt square, and fk2 is equals to k2 into y2 minus y1. So by Newton's second law, applied force is equals to sum of the reflecting opposing forces. that is fm2 plus fk2 is equals to 0. Therefore fm2 into d square y2 by dt square plus k2 into y2 minus y1 is equals to 0. On taking Laplace on both sides, m2 s square of y2 of s plus k2 into y2 of s minus y1 of s is equals to 0. We need to calculate the value of y1 of x. Therefore y1 of s is equals to y2 of s, by taking here y2 of s constant, y2 of s into m2 s square plus k2 by k2. So this is the value of y1 of s. So therefore y1 of s is equal to, we are taking it common, m1 s square plus bs plus k1 plus k2 minus y2 of s into k2 is equals to f of s. By taking y2 of s as common, okay, y2 of s is common, then it can be m2 s square plus k square by k2 and multiplied with m1 s square plus bs plus k1 plus k2 minus y2 of s k2 equals to f of s. Therefore y2 of s is equals to, after multiplying these values, okay, m2 s square plus k2 into m1 s square plus bs plus k1 plus k2 into k2 square by k2, which will be equals to f of s. Therefore the output function f of s, that is y2 of s is equals by f of s is equals to k2 by m2 s square plus k2 into m1 s square plus bs of k1 plus k2 and k2 square. So that's here. I'll stop the problems. In the next session we are going to learn some new interesting topics along with the problems. Thank you.